Hello students, welcome to lecture 45 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on applications of active hyperbolic metamaterials. So here is the lecture outline. We will discuss about two more applications of active hyperbolic metamaterials. One is supercollimation of terahertz light and the other one will be terahertz modulators. So let us begin with supercollimation of terahertz light in this lecture. So in the previous lecture, we have mentioned about three applications of active hyperbolic metamaterials. Among them, the first one we have already discussed in the previous lecture. So now we will move on to discuss the second application of the active metamaterials, hyperbolic metamaterials, which is basically supercollimation. Now, supercollimation at terahertz frequencies are particularly interesting, and it is an interesting feature because it enables super wavelength focusing, which is crucial for high resolution terahertz imaging, and other applications of this high resolution terahertz imaging includes security screening, biodetection, weather navigation, etc. Now, when I talk about supercollimation, which is also known as self-collimation, it is basically an optical phenomenon where a beam of light propagates through a specially designed material like a photonic crystal, or in this case hyperbolic metamaterial, without spreading out due to diffraction. That means it effectively maintains its width over a significant distance. So this occurs because of the material's unique dispersive properties that basically counteract with the natural tendency of light to diffract. So topological insulators based hyperbolic metamaterials offer tunable dispersion, which can be achieved by doping their surface states. So you can take example, and the most popular one that is known is bismuth selenide Bi2Ac3, that supports highly directional hyperbolic phonon polaritons. So we will come to these terms in the next few slides. So this basically enables supercollimation of light in the terahertz regime. So this particular material is very interesting, and that is what we will be studying here today. So bismuth selenide is basically a compound of bismuth and selenium, which is a 3D topological insulator that is made of selenium, bismuth, selenium, bismuth, selenium kind of quintuple layers. So the quintuple basically means that it consists of 5 parts or 5 things, right. So these layers are basically separated by insulating van der Waals bond. So in this particular figure here, you can see the layered structure of this bismuth selenide. Now this structure provides strong anisotropy in its phonon modes. So the phonon anisotropy that you will basically see in bismuth selenide arises from its crystal structure, and it affects both acoustic and optical phonons. So optical phonons are particularly interesting here. They are basically a type of phonon which are nothing but quantized vibrational modes of the crystal lattice. So they are characterized by the out of phase motion of atoms within the unit cell, meaning the neighboring atoms will vibrate in opposite direction. So this is basically the difference between optical phonons and the acoustic phonons, where all the atoms move in phase. So optical phonons becomes particularly interesting because their vibrational energy can be comparable to the infrared radiation, allowing them to interact with light, and that is why they got this name optical phonon. So the dominant phonon frequency you can observe from this graph, which plots the permittivity values. You will see something is happening along the x or the y axis, that is something happening here, which is 1.92 terahertz, and something also happening here for the Ez, that is the out of plane component, that is somewhere around 4.05 terahertz. Now, you can also quickly see that we will go into the details of the figure later on, but just by looking at it you can understand that this is plotting the real part of the permittivities, this is the imaginary part, the frequency dependence, okay, it is being plotting. So, it is also showing that the x and y components are equal, Ez, z component is different. So, it is basically a uniaxial material, okay, and these are all plotted for selenite. And what you can see is that the significance difference that you observe here between the xy component and the z component of the phonon frequency, that leads to extremely high anisotropic dielectric permittivities. So, as a result, you will see the real part of the uniaxial permittivity components, these are the real parts. Okay. So, epsilon x omega and epsilon z omega, which is this one, they basically become indefinite within a certain terahertz frequency range, and bismuth selenide basically exhibit hyperbolic dispersion in the terahertz range for TM polarized light. So, we will discuss the different kind of regime where it can operate as a hyperbolic metamaterial. Okay. So, in this case the dispersion relation of this material can be given as kx whole square plus ky whole square divided by epsilon z omega plus kz whole square divided by epsilon x omega equals omega square by c square. Now, to determine the uniaxial permittivity of this material, you can use a Lorentz-Drude oscillator model for estimating this anisotropic phonon polariton materials. Okay. So, in bismuth selenide you will see that phonon polaritons are basically a type of quasi particle that is formed by the interaction of light with lattice vibrations. So, that polariton is coming from the optical interaction with phonon. So, that is why it is a phonon polariton, right. So, these polaritons can exhibit unique properties due to the material's anisotropy. So, you can use this Lorentz-Drude oscillator model to understand and predict the behavior of this phonon polaritons in different directions. So, as the name suggests that this particular model combines the Drude model for free carriers and Lorentz model for bound electrons. So, it incorporates both the dynamic response of the electrons in material to electromagnetic field and also the effects of damping, right. So, for anisotropic materials such as bismuth selenide, this model is applied separately for different directions, accounting for the material's directional dependent optical properties. So, here is the model. So, you can use this particular dielectric function to write down the permittivity of this material along different directions. So, alpha here stands for x, y or z. So, we are just mentioning x and z because x and y are basically same in this particular case. You can see the direction x and y are basically the planar one and the z is basically the perpendicular one, right. So, epsilon alpha omega equals epsilon infinity alpha plus summation over j 1 comma 2, these are the two modes, okay. And then you have omega p alpha square j divided by omega alpha toj whole square minus omega square minus I gamma j alpha omega. So, what are these parameters? So, this basically tells you the frequency dependent permittivity along the direction x or z. Epsilon infinity alpha tells you about the high frequency static permittivity along direction alpha, okay. Omega toj is basically the transverse optical phonon, okay. So, TO is standing for transverse optical, this is the phonon frequency of mode J, okay. Alpha tells you about the direction, and wherever you will see P, that is basically the plasma frequency associated with that mode. So, omega p j alpha square tells you about the plasma frequency, and gamma is basically the damping or the phonon line width, okay. So, that is basically the collision rate, right. So, this is how you actually get the Lorentz-Drude oscillator model for modeling the permittivity of this material. Now, the values of these parameters that you see can be obtained experimentally from anisotropic 2-phonon dispersion model for bismuth selenide in terahertz region. Now, when you talk about a 2-phonon dispersion model for bismuth selenide in terahertz region, it basically focuses on the understanding of how pairs of phonons interact and contribute to the material properties in the terahertz frequency range. So, the model is critical for analyzing phonon dynamics, which are essential for understanding thermal and optical properties of bismuth selenide, particularly in applications such as thermoelectrics and different potential optical devices. So, in short, you can say that the phonon dispersion describes how the frequency of phonon, which are nothing but quantized vibration of the crystal lattice, varies with their wave vector or momentum. So, that is typically the definition of the dispersion, right. And the 2-phonon process that involves simultaneous creation or annihilation of 2 phonons, which can be crucial for energy transfer and relaxation within the material. So, now let us carefully see the plot. So, this is basically the plot of those permittivity that we have just seen the equation right now. Okay. So, here you can carefully see the real part epsilon x is nothing but epsilon parallel, as I mentioned, then x and y are equal and they are basically along the plane of the material. So, they are considered parallel, and epsilon z is basically the perpendicular one. Okay. So, you see that the sign with frequency, that means it supports different dispersion regimes, and imaginary part, this is the imaginary part and these are very large values. So, you can see the imaginary part is always positive, that means it basically behaves like a lossy medium. Now, let us identify the different frequency regimes in this permittivity plot. So, you have to compare and see this one when you have both epsilon x and epsilon z, that is basically the parallel and the perpendicular one, both are positive. That means it behaves like a dielectric. So, that you can mark as region A, okay, that is the dielectric band. Then you have region B where the parallel part becomes negative. So, this is the 0 line. So, this is where the parallel part becomes negative, the perpendicular one remains positive. So, that is where it behaves like type 2 hyperbolic band. Okay. So, you can mark that region as B. Okay. So, this is basically the dispersion curve. So, omega k, and then you can write down the region. Okay. Then you have epsilon x is negative, epsilon z also negative, both are negative. So, that is called rest Strahlen band. So, this rest Strahlen band basically refers to a specific wavelength range where a material basically exhibits strong absorption and high reflectivity. Okay. So, in this particular region you will see that the absorption is also very high, and because the permittivity is completely negative. So, it is very highly reflective material, particularly in this infrared region, right. So, this occurs due to the interaction between the electromagnetic radiation and the optical phonons, which are nothing but the lattice vibrations within the material's crystal structure. So, the rest Strahlen, that is basically the residual rays band, is a spectral region where you can see the materials basically become highly reflective for the electromagnetic waves, and that basically comes from the phonon polariton resonance. Okay. So, especially in ionic crystals such as silicon carbide, aluminum nitride, gallium nitride, and topological insulators like this bismuth selenide, you will see this kind of effect. So, this basically lies between the transverse optical and the longitudinal optical, that is TO and LO phonon frequencies of the material. And the last band, that is where you will see that your epsilon x, that is the parallel one, becomes positive and the epsilon z becomes negative. So, that is the type 1 hyperbolic material, and that region you can mark as region D. Now, let us focus one by one. So, we have seen that the region B is marked as this one, that is where you have type 2 hyperbolic band because your parallel permittivity is negative and perpendicular permittivity is positive. So, it has got a bandwidth of 2.14 terahertz. So, it basically starts from 1.91 to 4.05 terahertz. So, it has got a very wide bandwidth. This band is relatively new, the regions narrow. The Australian band, that is region C, has a bandwidth of only 0.35 terahertz, where both are negative. So, that basically lies from 4.05 to 4.4 terahertz. And the region D, that represents type 1 hyperbolic metamaterial kind of behavior, where you have epsilon parallel positive and epsilon perpendicular negative, that has also got a narrow bandwidth of 0.3 terahertz, ranging from 4.6 to 4.9 terahertz, right. So, what is the main key site in this particular discussion? You have seen that barium selenide based hyperbolic metamaterials can support both type 1 and type 2 hyperbolic metamaterial dispersion in this terahertz regime. So, that tells you that bismuth selenide can support highly directional, deeply subdiffractional hyperbolic phonon polariton modes. Okay. So, that will basically allow you supercollimation and superlensing applications. So, in hyperbolic metamaterials, we have already seen this concept, but here we will focus on it even more, that the wave propagation occurs only within the resonance cone, which is called RC, okay, that is defined by the hyperbolic dispersion. Now, a resonance cone basically refers to a specific angular distribution of the electromagnetic energy that arises due to the unique anisotropic properties of these materials. Specifically in hyperbolic metamaterials, the resonance cone basically describes how electromagnetic waves propagate, creating a cone shaped energy distribution around the source. So, you can calculate the half of this resonance cone angle alpha RC from tan inverse square root of epsilon x omega divided by epsilon z omega. So, epsilon x omega is nothing but the epsilon parallel, it is the in plane or you can say lateral permittivity, and epsilon z omega is nothing but out of plane or vertical permittivity. Now, what is the condition for supercollimation? You will see that supercollimation, okay, means the parallel wavefront or the propagation of the light beams will occur when alpha RC becomes 0. That means, this term becomes 0, and that is possible when your epsilon x omega will become 0 or epsilon z omega will become infinity. Okay. So, the figure 2 basically shows a plot of this alpha RC as a function of terahertz frequencies for this bismuth selenide material. So, here you can see the minimum RC is happening somewhere close to this 4.05, that is almost close to RC equals 0 degree, not exactly, but very close. So, this is the transition point between the type 2 band, type 2 hyperbolic metamaterial band, and the domain C, that is your Australian band, right. So, you can see that the supercollimation effect in this material bismuth selenide will take place specifically at this frequency 4.05 terahertz, and this is because that your resonance cone angle is almost nearly 0 at this frequency. Now, what will happen if the resonance cone angle increases? You will see that the spectrum will get broadened and you will reduce the collimation. So, here you can see the line profile of the normalized intensity that is recorded at the bottom of the quintuple layered bismuth selenide. So, here you can see exactly at that angle exactly at 4.05 terahertz, where alpha RC is almost 0, you see it is very narrow, but as soon as you move little away from this at 4.6 terahertz, you can see the intensity spectrum basically broadened. So, that will reduce the collimation. So, the supercollimation frequency can also be tuned by adjusting the inversion point between this type 2 band and the Australian band, and that can be achieved by doping the surface states of the bismuth selenide, right. So, that is the application that you have seen from the supercollimation aspect from this hyperbolic metamaterials. Next, we will move on to terahertz modulators. Terahertz modulators are essential components in terahertz communications, spectroscopy and imaging. The modulators can be created by integrating photonic structures with tunable conductive materials such as semiconductors, superconductors, perovskites, 2D materials such as graphene, MOS2, different phase change materials like VO2 and liquid crystals, right. So, there are two types of terahertz modulators based on solid state and non-solid state with broad or narrow bandwidth responses. So, among which you will see that the narrow bandwidth terahertz modulators typically rely on resonant effects which are enabled by the metamaterials or plasmonics, and they are often realized using this kind of solid state or non-solid state platforms. So, if you focus on narrow band terahertz modulators, okay, they will require intensive lithography processes because they are based on metamaterials and plasmonics. You have to make that resonator kind of structure that will give you that narrow bandwidth feature. The other one can be the broad bandwidth modulation. That is important for many applications, and it can be achieved by non-resonant and graphene based solid state devices, okay, because it depends on non-resonant materials. That is why you get a broad bandwidth. Okay. So, active control of terahertz modulators with high intensity and phase tunability is critical for many applications, and when we talk about high performance terahertz modulators, they should have high modulation depth. Okay. So, the difference between the high state response and the low state response should be really large. Okay. You should have broad operational bandwidth and high modulation speed. Active control of polarization state of the light across different spectral bands also has wide applications in optics, right. For effective reflection type active polarization switches, the following two conditions must be met. So, one thing is that now the S polarized reflected intensity must remain unity with or without external stimulus, and for the P polarized reflected intensity at resonance, it must have nearly 100% modulation depth. That means, it will enable active switching. So, you can see that achieving 100% modulation depth at terahertz frequencies could be challenging, right. So, what is the proposed solution in this case? You can think of a terahertz modulator or active modulation switch based on high critical temperature superconductor hyperbolic metamaterials. Okay. So, when you say high critical temperature superconductor, they basically refers to superconducting materials that become superconducting at relatively high temperatures, typically above 30 Kelvin as compared to the conventional superconductors. Now, in hyperbolic metamaterials term, this critical high critical temperature superconductors can be used as components to achieve low loss and tunable terahertz response. So, one example of this kind of high critical temperature superconductor which has got a TC of around 90 Kelvin is this YbCO, yttrium barium copper oxide. This is the chemical composition of that. So, how it works? Below this critical temperature, YbCO exhibits a metallic behavior that can be characterized by its negative permittivity. So, making it suitable as a metallic layer in the metamaterial, and in that case, so it can also excite the Brewster mode, okay, for this hyperbolic metamaterial, and that can enable over 98% intensity modulation and 100% of phase tunability. Now, when we talk about Brewster mode in hyperbolic metamaterial, these are a way to excite and utilize the unique optical properties of these materials for sensing and other kind of applications. Like hyperbolic metamaterials with their anisotropic permittivity exhibit unusual wave propagation characteristics, and Brewster angle is where the P polarized light is not getting reflected. So, that plays a crucial role in their behavior. So, by exciting Brewster modes, enhanced sensitivity for refractive index sensing can be achieved. So, hyperbolic metamaterials can be designed to act as intensity and phase modulator for terahertz light by tuning the Brewster angle. Okay. So, that is where you can achieve this kind of 98% intensity modulation or 100% phase tunability. In doing so, temperature variation can be used as the external stimulus that can give you this active control of the properties. Okay. So, the YbCO, that is yttrium barium copper oxide, and LaO, that is lanthanum aluminate. This hyperbolic metamaterial is basically a type 2 hyperbolic metamaterial, which is shown here. Okay. So, this structure basically exhibits hyperbolic dispersion in a specific frequency range. So, you have got the perpendicular one to be positive and parallel one to be negative, that is why it is type 2. Okay. So, you can see a unpolarized light incident on this HMM splits into S and P polarization, and the reflected lights are also S and P polarized. Similarly, the refracted ones will also be, right. So, when you talk about type 1 HMM hyperbolic metamaterials, they basically support Brewster mode because of their real parallel component of the permittivity to be positive. Now, if you look for type 2 HMMs, they basically do not support Brewster angle because their real part of the parallel permittivity is negative, right. As you can also see here that those are negatives. However, it can enable terahertz intensity and phase modulation when the incident angle is near the Brewster angle. Okay. So, in this case, for this kind of material where you have alternating layers of YbCO and LaO. So, YbCO will behave like metal because the parallel one is negative and the perpendicular is positive. So, LaO is also behaving like the dielectric. So, this is the multilayer anisotropic medium, okay, and this structure is tunable using temperature across your critical temperature or using some magnetic field, okay, which is useful for terahertz modulator, super lens or even quantum devices. So, let us look into the modulation principle for this kind of device. So, this is, as I mentioned, this is the YbCO and LaO type 2 HMM, and we will see the principle of the Brewster angle effect in it. So, the transition from elliptical dispersion in the dielectric phase to a type 2 hyperbolic dispersion, that is in the superconducting state, happens in this particular material. So, the dielectric phase of this YbCO is where the Brewster mode is supported, and that allows modulation of both intensity and phase of the terahertz light. So, this can be achieved by temperature tuning across the semiconductor transition temperature. So, the playing with TC is an important role, right. So, as you understand, the dielectric phase of the YbCO is basically working for you here. So, you can modulate the phase and intensity of the terahertz light using this concept. So, with that we will stop here and we will discuss about active hyperbolic metamaterials in various spectral bands in the next lecture. So, if you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.